Hello, this is Tarina Ahmed. Today I will talk about transistor scaling beyond 10 nanometer node. The first question that comes to mind on this topic is why do we scale transistors? In 1974, Dennard suggested that if all device parameters are scaled by the same factor alpha, that is gate oxide thickness reduced by alpha, channel length increased by alpha, source drain junction depth decreased by alpha, channel doping increased by alpha, and supply voltage decreased by alpha, the result would be an increase in device packing density, improvement in frequency, power circuit would be reduced. Power density would remain constant and current drive would be improved. In essence, with scaling, gate delay would decrease and performance would increase. This has served us well for multiple decades. Unfortunately, we have now reached the limit where Dennard's law does not hold anymore. So what is these issues? As thickness of silicon dioxide goes below 2 nanometer, tunneling effect comes into picture, which causes large leakage current. Because of depletion layer formed between poly and gate dielectric, additional capacitance is formed in series, which increases the equivalent oxide thickness. That is, equivalent thickness of gate dielectric that can produce same current, reducing performance. The high electric field in the channel due to the reduced gate length causes mobility degradation and reliability issues. Scattering increases, saturating the velocity of electrons earlier than saturation drain current. Drain-induced barrier leakage causes drain to source leakage, and short channel effect causes increased off current. At source and the drain, parasitic resistance increases with the scaling, decreasing on current. Finally, leakage current from reverse bias diode formed at drain to substrate junction can reach to channel and make poor electrostatic control over channel. The net result, bulk silicon CMOS device performance increase commensurate with size scaling is unlikely below 65 nanometer. So the semiconductor industry has come up with solutions. High mobility channel and strain engineering helped with the poor channel transport issues. High-K dielectrics were introduced to solve gate leakage due to tunneling. Metal gates were introduced for tackling gate depletion. Metal silicides helped reduce SD resistance issue. And finally, introduction of non-planar structures such as FinFETs allowed to improve gate electrostatics and move to the 22 nanometer node. It is clear that materials research has been paramount in achieving this, and we are seeing more and more non-silicon elements being introduced into transistor technology. Also, these solutions are patches enabling the industry to progress for a decade or so, maybe to the 7 nanometer regime. But for a continued momentum forward, disruptive technologies are also being researched. One promising technology is carbon nanotube FETs, or we call it CNTFETs. So what are CNTs? They are hollow cylinders of hexagonal arranged carbon atoms. CNT is composed of a single cylinder are known as single wall CNT, and those composed of multiple cylinders as multi-wall CNTs. The SWCNT can be thought as of being formed by folding a piece of graphene sheet, that is a layer of graphite, to give a seamless cylinder. The circumference of the CNT is expressed by the so-called chirality vector, connecting two crystallographically equivalent sides of the two-dimensional graphene sheet. Depending on the chirality of the CNT, one can determine if the characteristics of the CNT would be semiconducting or metallic. CNTs with the zigzag chirality are semiconducting, whereas those with armchair chirality are metallic. There are various ways to synthesize SWCNTs. Arc discharge, electrolysis, chemical vapor deposition, laser ablation, and sonochemical or hydrothermal. The first CNTs were synthesized by arc discharge. Here is a shown CVD process to create CNTs. A nanoporous alumina catalytic layer is used as a template and using CVD and AAO template etching process, the CNTFETs are formed. Here is an ACM image of a CNT forest created using PECVD process. So the next question that comes to mind is why CNTs are the material for the next generation FETs. CNTs have some properties that make it suitable for replacing silicon in FETs. They have one-dimensional carrier transport. So there is reduced phase space for carrier scattering and possibility of ballistic transport. Power dissipation is low and short channel effects such as electron hole tunneling, gate leakage current, and punch-through effect are reduced. All chemical bonds of the C atoms are satisfied, so there is no need for passivation of dangling bonds in silicon. So possibility of using insulators other than silicon dioxide opens up, and 3D fabrication can be undertaken. CNTs have very high thermal and mechanical stability and resistance to electromigration, supporting current densities up to 10 to the power 9 ampere per centimeter square. The key dimension of CNTs are their diameter, which is determined by chemistry. So, lithography does not pose to be the barrier of developing CNTs with smaller and smaller diameters. Finally, there are both semiconducting and metallic CNTs, allowing for both transistors and interconnects to be made out of CNTs. CNTFETs also have some added advantages. Because CNTs have symmetric conduction and valence bands, symmetric NFETs and PFETs can be made. They can be arranged in parallel to achieve higher mobility channel, high on current for same off current. Also, CNTFETs can reach higher frequency domain, kind of terahertz regime. CNTFETs do not have short channel effects. They have higher transconductance and lower power dissipation than conventional MOSFETs. The first CNTFETs were P-type SB CNTFETs. N-type was obtained by direct doping of the tube with electropositive element or simple annealing process of P-type CNTFETs. The metal CNT boundaries introduce the Schottky barriers, which can be modulated by the application of gate voltage, and thus the transconductance of the device depends on the gate voltage. The PG CNTFETs are either uniformly doped or intrinsic, partially gated, and with ohmic contacts at the ends. They can be either N-type or P-type depending on doping. The uniformly doped device function in depletion mode and the on current is limited. The intrinsic devices function in enhancement mode and can be N-type or P-type based on tunable electrostatics. Doped SD CNTFETs are made up of a partially gated channel area with two doped ungated portions at the ends acting at the source and the drain regions. These are unipolar P-type or N-type devices function in enhancement mode or depletion mode. The gate voltage modifies the potential barrier right, thus controlling the on current. The first CNTFETs were fabricated with a single wall CNT used to bridge two noble metal electrodes prefabricated by lithography and an oxidized silicon wafer. The SWCNT was the channel, the metal electrodes were the source and drain, and the heavily doped silicon wafer was the gate. These P-type CNTFETs were called backgated and had high parasitic contact resistance, which is around 1 mega ohm. Low drive currents, around a few nanoamperes, and low transconductance. The next generation CNTFETs were top gated. After forming the horizontal CNTs on silicon oxide, contacts are formed for the source and drain regions, followed by gate dielectric, and finally the gate. Further advancements led to the development of coaxial CNTFETs, where the gate wrapped all around the channel. This geometry allowed for better electrostatics and very good control on carrier transport. The type of metal CNT contacts again plays a crucial role, and heavily doped semiconductors can be used to form ohmic contacts. However, these still suffer from high parasitic resistance. Vertical CNTFETs have also been developed, and here is a schematic and image of these vertical CNTFETs. These characteristic graphs and figures drives home the point that CNTFETs outperform MOSFETs at the 32 nanometer node. The first figure shows that the on current are independent of length and width variations for CNTFETs. The maximum leakage can be seen to be orders of magnitude lower for CNTFETs. The table shows the gate delays, power dissipation, and leakage for various gates made from MOSFETs and CNTFETs. The gate delays, power, and leakage figures are all better for CNTFETs. So, what are we waiting for? Why not switching to CNTFETs? There are actually various challenges that are there today. Large-scale fabrication challenges is one of the major factors. CNTFETs require SWCNTs and the selective growth of SWCNTs over MWCNTs. This is a challenge even during CVD process. Also, selective growth of semiconducting CNTs over metallic CNTs is a process yet to be perfected. Traditionally, constructive destruction techniques were used to selectively destroy metallic CNTs. Also, the issues of controlling chirality during manufacture reliability is harder to be overcome even today. The self-aligned fabrication methods used to create CNTFETs suffer from reliability issues. In doped SD CNTFETs, control doping of the source and drain region is very difficult, and ion implantation techniques cannot be used as ions may replace carbon atoms and destroy nanotube properties. There are various device modeling challenges as well. For one, SB CNTFETs exhibit strong ambipolar characteristics which are hard to model. Nanoscale fabrication brings with it higher defect and fault levels than current CMOS technology. It is assumed that 1 to 15% of the resources on a chip will be defective. Deterministically placing all parts of a circuit in nanoelectronic devices will not be possible, and stochastic assembly will be necessary. And reliable manufacturing is naturally difficult, mainly due to the stochastic assembly. Given all the benefits of CNTs in the field of electronics, and given that it will overcome all the challenges, there will be a final resistance in terms of business inertia from the heavily silicon process invested industry. Silicon Valley, the center of the high-tech world of integrated circuits and headquarters of the leading chip makers such as Intel and AMD, and leading consumer electronics companies such as Apple, HP, derived its namesake from silicon-based technology. So it will be difficult to move these multi-billion-dollar operations to a completely new process technology quickly and without any resistance. In summary, we have seen how transistor scaling below 14 nanometer poses many challenges. We have gone over how the semiconductor industry has elongated the life of the silicon CMOSFET with various techniques to reach the sub 10 nanometer nodes. We have seen how CNTFETs are an exciting prospect to replace silicon CMOSFETs. Finally, we have seen how these replacements may not be immediate due to the challenge that lie ahead for CNTFETs. So here are the list of references used in this work. Um, so hope you enjoyed the presentation. Thank you.